Okay, very good morning. What we will do today is conclude our discussion on autoregressive models and then briefly talk about ARMA models, and then hopefully we will have the time to move on to non-stationary models where we will look at how to handle trends and integrating effects, where eventually we will be led to ARIMA models. But today let us begin with from where we left off yesterday. So, we said that the ACF of the autoregressive models can be obtained by setting up the Yule-walker equations and then solving accordingly for the p up to lag p, and then lag p onwards you use the difference equation form if needed. And these Yule-walker equations can also be used to estimate the model parameters, as we have discussed yesterday. In practice, what you do is you use these Yule-walker equations even on the estimates of the ACFs, and later on we will study how good these estimates are. We have both for moving average and autoregressive models when we get into estimation. Okay. So, a significant part of modeling exercise, the effort goes into determining the order of the model, whether it is autoregressive or moving average or any other model that you are fitting to data. This so called order really is very important, and we know already with respect to autoregressive models the ACF does not provide any clear information on what the order is, and to that effect we have looked at PACF, right. So, we will just dwell a bit more on that and talk about the connections between PACF and the autoregressive model of order P. We have I mentioned this before, that the PACF at lag L is the last coefficient of the autoregressive model that you fit of order L. We will reiterate that point today. So, in general, if you look at keeping aside PACF concept, if you were to determine the order of autoregressive processes, there are two ways of approaching this problem. One is of course to try out AR models of different orders, right. So, you begin with AR1. In general, how do you determine, for example, if a model order is suited to the data or not? What is the generic procedure for the test of a model? It could be MA, it could be ARMA, does not matter. Any model that I fit, how do I know if I have reached or I have guessed an appropriate order for the data? Sorry? Residual should be wide, correct. So, what you do is here also you fit AR models of successive orders, right, and then as you move, as you fit an AR model of a certain order, examine the residuals. If they are satisfactory, then you stop. If they are not, then you successively increase until you reach a point where you say, yeah, I have kind of reached the so called true order or the appropriate order. Now, that is the basic idea also that you will see essentially in the PACF. The other approach is to of course discount for the propagative effects in ACF, which leads us to PACF. It turns out that both of them are actually equivalent to using PACF only, although on the face of it they appear to be different. Computing PACF essentially looks at essentially amounts to fitting AR models of successively increasing orders. Intuitively, if you look at the PACF, how are we estimating the PACF? We can discuss from lag 2 onwards, because at lag 1 anyway PACF is same as the ACF. So, at lag 2 what am I doing? I am actually discounting. I fit a model, first order model AR for Vk, right. So, let us call this as phi 11 and plus some epsilon k, right. We hope if we force fit, we kind of pretend that the residuals will have white noise characteristics. One has to test later on whether indeed this is the case. So, we fit an AR1 model for forward model, and we also fit an AR one model backwards, right. So, we have, let us say, let us call this as maybe phi tilde phi phi 1 1 V k minus 1 plus E tilde k. This is not necessarily going to be correct, we do not know, we will have to figure out. But to compute PACF at lag 2, whether you are doing this explicitly or not, this is what you are actually doing implicitly. You are fitting an AR1 model for Vk, a forward model and a backward model, and then you are going to work with these residuals. So, in place of Ek, suppose I had epsilon, just to be more generic. So, I have epsilon and epsilon tilde. After having fit the forward and backward models, then I am going to look at the correlation between epsilon k and epsilon tilde of k, correct. So, what you are actually looking at is also the residuals of autoregressive models. When you move on to the PACF at lag 3, again you are going to fit an AR2 model, a forward AR2 model and a backward AR2 model, and then you are examining the residuals. At some point, if you have hit the so called true order, then there will be nothing in the residuals, and what you have managed to do is, between the PACF at lag L and lag L plus 1, let us say you have hit at L plus 1, what you have managed to achieve is explain the process perfectly by an ARL minus 1 model. In the sense, here of course, we are looking at lag 2, so you are fitting AR1. When you move on to lag 3, you will fit an AR2 and so on. So, what you manage, when you reach the true order, you have managed to explain the process by an ARL model. Okay. So, that is the basic idea. Anyway, let us look at it more in detail now. So, this is how you would fit, this is the procedure that you would follow when you were to fit successively increasing orders AR of that is orders in the sense of the autoregressive models, where you do not have to worry about the PACF concept itself. You just say, well, I am going to do a trial and error, I am going to fit an AR model of successively increasing orders and keep track of the last coefficient, and essentially the value of P, after which you start seeing the last coefficient that you have included turning out to be negligible, you say, yeah, I kind of hit the true order, because the inclusion of any further order has not helped in any significant way, that is the idea. But there is a premise underlying this, I mean we need a theoretical backing to this result. What we are claiming here is, if the model or if the process is of some order, let us say third order, and I fit a fourth order AR, then the extra coefficient that I have included should theoretically turn out to be 0. That is the premise on which this method works, this successively increasing order method works. We are claiming that as I successively increase the order, and when I hit the correct order and I go beyond that, then the extra terms that I have included do not contribute, at least theoretically do not contribute, or you can say practically do not contribute in a significant way. So, we need to prove that theoretically, although I am not going to prove that here, it is not so difficult to prove, but I will state the result. The result is, when an ARP model is fit to a process of order P naught, right, then the additional coefficients that you have included, additional meaning in excess of the true order, they all turn out to be 0. How do you prove this? Well, you can, in one way you can prove by setting up the Yule-walker equations and show that they turn out to be 0, taking into account the fact that the underlying process is AR of order P naught, right. When we say, when the for example, if I say P naught is 1, that is the underlying process is a first order AR, and I fit, let us say, a second order. And so, this premise here, the theory, the underlying philosophy or the result says that the second coefficient of this AR2 model is going to be 0. what is the model symbolically? Vk is phi 2 1 Vk minus 1 plus phi 2 2. Here we are not using the coefficients d's, because generally we reserve the notation d for a given AR process. Here we are trying out different orders. So as to keep track of the different orders, we introduce this phi notation. This is fairly conventional in time series literature to use this notation phi. So the first subscript here denotes the order that I am fitting, and the second subscript here denotes the coefficient. So I am fitting a model of this form when I say I fit a second order AR, and what this result claims is, if the process is first order AR, then phi 2 2 is 0, if this is true. How do you see that? What you do is you set up the Yule-walker equations, right, for phi 2 1 and phi 2 2, correct. So what would be the Yule-walker equation? So we can go back to the Yule-walker equations that we had here. For example, in this here we have d1 and d2. In place of d1 and d2, you can have minus phi 2 1 and minus phi 2 2, right. What would be the value of d2? Let us say if d2 is 0, then phi 2 2 is also 0. For an AR1, the equations that you set up in Yule-walker equations are fairly generic for a generic AR process, but if you are given that the underlying process is AR1, so from these equations here, what is the value of d2? the generic solution, symbolic solution. Sorry? So d2 would be, you remember Kramer's rule? When you want to selectively estimate coefficients, you can use Kramer's rule, right. What is Kramer's rule, by the way? You replace one of the columns, the corresponding column with the right hand side, and then of course then you always have the determinant in hand. So the determinant is 1 minus rho 1 square, which appears in the denominator for d2. What about the numerator? Sorry? Rho 1 square minus rho 2, or we can, in order to connect it with the PACF, we can say it is rho 2 minus rho 1 square. I am using a different notation here, it is a subscript, it should be at lag 2, but you should understand. Now this is a this is a generic solution for fitting an AR2 model to any process. If I fit an AR2 model to any process, this is the value of d2. Until this point, we have not made any assumptions on the underlying process. If the underlying process is AR1, then you would want to ask what is the value of d2, which is nothing but your minus phi 2 2, they are the same except with a difference of sign. So if the underlying process is AR1, what is the value of d2? Why? Because if the underlying process, let us say, is first order with some coefficient d1 naught, right. So we have said p naught is 1, let us say the coefficient is d1 naught. This is how the underlying process evolves. Therefore, what would be rho 1? So this implies rho 1 is minus d1, and rho 2 would be d1 square, sorry, d1 naught here, d1 naught square. So you plug in this values, theoretical values, into your d2, and you can straight away see that this extra coefficient that you have included in excess of the true order has turned out to be 0. This is not coincidental, you can show this now for any AR process of order p naught. If you fit a model of order p for to a process that is being generated by p naught, then the excess coefficients are going to be 0. That is the basic idea. and that is also the basic idea for using PACF. Okay. So, hopefully now at least you are convinced by way of example that the excess coefficients turn out to be 0. In fact, what you should go back as a simple exercise and do is set up the Yule-walker equations for an AR3 model. Model would be AR3, fix the process to AR1. For the same process, first order AR, fit an AR3 model and see if the third coefficient also that you have included turns out to be 0. Okay. Now, of course, as I said, you can increase, you can actually estimate AR models of any order using Yule-walker equations, but there is an additional benefit of this approach of fitting AR models of successive order, which is that you can come up with a recursive way of estimating the autoregressive models of increasing orders. You do not have to solve the Yule-walker equations all over again. So, if I have, for example, worked out the estimate of a first order AR for a given process, and I want to now fit an AR2 and I want to see if AR2 is better suited than AR1, then I do not have to necessarily solve those two equations that we saw earlier all over again. I can use a recursive relation, and this applies to any order. If I know the coefficients of the AR model of an order P, then the coefficients of an AR model of order P plus 1 can be computed recursively, and that was the algorithm given by Durbin and Levinson, and today it is known as Durbin-Levinson's algorithm. So, what you do is you start off by fitting an AR model of first order. I mean that is no big deal, it is nothing but the optimal estimate, even from a least squares viewpoint or a Yule-walker equation viewpoint approach. The optimal estimate of the coefficient is rho at 1, the ACF at lag 1. Now, the coefficients of AR models of successive orders that you have, that is increasing now second order, third order and so on, can be computed recursively using the equation that is given on the screen. That is the recursive relation due to Durbin and Levinson. So, how do you work this out? What it says is, if you have an AR model of order P, first you estimate the last coefficient of the next higher order model. Do not be confused here. This is an AR model of order 2. What you would have estimated is an AR model of order 1. Let me erase this. You would have estimated this phi 1 1 Vk minus 1, okay, plus some Ek. Do not get confused between these two E's, they are actually different. So, focus on the coefficients here. You would have estimated this, and now you want to estimate phi 2 1 and phi 2 2. And the algorithm says you can do it in a recursive manner without having to solve the Yule-walker equations all over again. And what the algorithm says is, start off by estimating phi 2 2. Once you have estimated phi 2 2, get the estimate of phi 2 1. Do I need phi 2 1? Yes, if you want to if I want to estimate an AR model of order 3 and so on. But if I have decided to stop and I just want to know the order, then I do not need those other coefficients, but typically we would need, because once we have hit the true order, then you may want to actually know the remaining coefficients, but typically you want to know the remaining coefficients of the previous model. For example, here for this process we have just now shown that if the underlying process is AR1, phi 2 2 will turn out to be 0, right. Then what is the correct model order? 1. So, I have to go back and use phi 1 1, I should not use phi 2 1. That is a very important subtle point to remember. Once I have hit the true order, I should work with the previous AR model, because it says you have crossed the line. You have crossed the line and realize that that there was a line. So, you have to go back to that line and then use the coefficients there, right. In other words, here if you discover that phi 2 2 is 0, in fact you can't stop at phi 2 2 being 0, it may be just that one coefficient can work out to be 0 for some processes. You have to make sure that persistently phi 2 2 and then phi 3 3 all, when you have to move on to AR3 and check that phi 3 3 is also 0 and so on, at least until a few lags. Then you come back and say what is the first time I cross the line, and I cross the line here in this example at 2. So, I go back to first order and use phi 1 1 for my model. You can't use phi 2 1 because that is assuming that you are going to work with AR 2. Okay. Theoretically phi 2 1 may be same as phi 1 1, but practically it will not be, because what happens is in estimation, depending on how many parameters you are including in your model, estimates will change, and so will the errors. So, therefore, you have to go back to the previous model and then work with that. So, that is the idea. So, if you look at the equations carefully, what it does is it estimates phi 2 2 first, and then the second relation there allows you to estimate phi 2 1. When you are done with that and you want to move on to third order AR, then you estimate phi 3 3 first. With the help of phi 3 3, you would estimate phi 3 1 and phi 3 2, and so on. So, as an example, I do not know if I have, so let us, I will come back to the PACF. So, keep aside PACF fact, let us look at how you would estimate given phi 1 1, how do you estimate phi 2 2. So, go back to your Durbin-Levinson's algorithm. If I am given phi 1 1, I already know from the previous discussion that phi 2 2 is essentially this, right. We have already solved for it, we did not use a recursive relation at that time, we solved the Yule-walker equations all over. Now, let us see if the Durbin-Levinson's actually is giving me that. So, if you look at the relation there, it says phi at p plus 1 comma p plus 1, that is phi 2 2, p is 1, would be rho at 2 in the numerator, the first term is rho at 2 minus how many terms do you have in the summation? 1, and that happens to be phi 1 1 times rho 1, but phi 1 1 is already rho 1, right. So, you have rho 1 square, and in the denominator you can straight away see you have 1 minus rho 1 square. So, you do get that, right. Of course, this algorithm has been proposed and verified many times, it has been theoretically derived, and you can also see that it allows you to derive phi 2 1. What would be phi 2 1? It says phi 2 1 is, so let us write for phi 2 1 using the DL algorithm without solving the Yule-walker equations. What do you get for phi 2 1? Phi 1 1 minus what do you get? Why is it so difficult? Sorry, phi 2 2 times phi 1, and you should verify if indeed you get this as the answer. Yeah, I have just left it at in terms of phis, you can substitute for phi 1 1 and phi 2 2 and see if you indeed get the same from the Yule-walker equations, right. That is a very simple exercise, and this is now the algorithm also that is used to estimate the PACF coefficients. How? Because there is a strong connection with this approach and the PACF. And what is that connection? As I said earlier and even previously, the last coefficient, if I want to estimate PACF at lag L, then I fit an AR model of order L and pluck out the last coefficient. Okay. So, which means phi 2 2 is nothing but the PACF at lag 2. Phi 1 1 is obviously the PACF at lag 1. PACF at lag 3 would be phi 3 3 and so on, right. Now, if I want to compute, so this proof itself I am avoiding, but I think you would have seen by now, in the sense when you set up those equations for PACF, computing PACF, and you compare with the successively increasing orders methods, you will be able to prove very easily that the last coefficient is nothing but PACF. Okay. Intuitively you can look at it this way, when you look at this model, what is phi 2 2 measuring? What is actually phi 2 2 measuring? It is measuring the impact or influence, linear influence of Vk minus 2 on Vk in presence of Vk minus 1. And that is what PACF is also trying to do. I mean, I am just giving you a very strong qualitative proof here that this phi2 that you are looking at in an AR2 model is actually measuring the linear influence of Vk minus 2 in presence of Vk minus 1. Phi2 is not measuring the direct the linear influence of Vk minus 1 on Vk directly. It is directly doing, but it is not PACF at lag 1. It is definitely measuring the sole influence of Vk minus 1 on Vk given the conditioning variable being Vk minus 2. But that is not PACF at lag 1. PACF at lag 1 is nothing but ACF at lag 1. So, you have to understand the notion of PACF clearly. The PACF is nothing but the correlation or the measure of linear influence between Vk minus L and Vk conditioned on all intermediate observations, not any other future observation. So, in other words, if I move to a third order, I would have phi3 and phi3 and a phi3, right, plus Ek. So, when I move to the third order model, you can't say phi3 is the PACF at lag 2, obviously, because PACF at lag 2 is only looking at discounting for the effects of Vk minus 1, it is not discounting for the effects of the other sample, only the intermediate ones, because it is looking at the time chain. So, phi3 is now measuring how much Vk minus 3 is directly influencing Vk in presence of Vk minus 1 and Vk minus 2. So, that kind of convinces you that indeed the last coefficient of the AR model has to be the PACF. Okay. So, using this connection and the Durbin-Levinson's algorithm, now we can compute PACF in a very recursive manner, computationally efficient manner. Yes. Okay. P is 1. It depends on where you are. If you are fitting, in the first step you assume that you fit in AR1, right. So, the coefficients of ARP models of orders, oh I see, P greater than or equal, that is the confusion that you have. Yeah, so you look at it this way, disregard the statement P greater than or equal to 2 there, sorry for the confusion. The way you use the recursive relations is, it says if you have coefficients of ARP model, then how do you estimate ARP plus 1, okay. So, I will make that small correction, I understand the source of confusion. Is it clear? Right. So, I will take away that P greater, I will just say of orders greater than or equal to 2. Any other question? Okay, I am glad you are watching the notes quite closely. Right. So, now with this connection we have a recursive or a computationally efficient algorithm for computing PACF, and that is what your PACF routine in R or any other package ideally uses. It uses a DL algorithm. Not only this does this DL algorithm give me a computationally efficient way of computing PACF, but even for estimating AR models, right. The DL algorithm was devised in general for any AR for estimating any AR model of a given order by knowing the AR model of the previous order. So, it has it does not bind itself to PACF. PACF happens to be only a small piece of information that, but an important piece of information that you are extracting out of the AR model. So, one keeps track when you want to compute PACF, one keeps track of these chain of coefficients. Okay. So, that is a generally and widely used PACF algorithm for recursively computing PACF. We have gone through this, I am going to skip. So, that kind of brings us to the conclusion of the discussion on autoregressive models. We have discussed what an autoregressive model is, that is how does it take birth from the linear random process, and it takes birth whenever we assume a certain kind of parameterization for the impulse response coefficient, and that parameterization is nothing but an exponentially decaying one, and parameterization of IR coefficients is the same as parameterization of the ACF as well. So, you might as well say an autoregressive model is that whose ACF is parameterized to decay exponentially. And of course, another way of looking at autoregressive model of orders P is that any information that you give beyond P lags is not going to make any difference in my forecast. That is another way of looking, that is from a prediction viewpoint. And there are several advantages of working with AR models. It gives rise to linear forecasts, linear predictors, sorry. Unlike MA models, where I have to go through this additional step of figuring out what the shock wave is in order to complete the forecast. But then order determination requires a computation of PACF. Although you can say it is PACF, what you are actually doing is, as we have discussed just now, you are fitting AR models of successive orders and you are computing it in an efficient way, that is all you are doing. But conceptually PACF is a conditioned correlation. Conceptually this approach of fitting successive orders and PACF are quite different. The notion of conditioning there appears, but now you can see the notion of conditioning amounts to actually fitting models itself, linear models itself. So, for example, here when I am computing PACF at lag 2, what I am actually doing is multiple regression, multiple linear regression. I have many regressors, but some specific regressors when I am looking at PACF. And then we discuss the issues of stationarity. We said that even though the underlying process has a non-stationary causal representation, I can give a stationary non-causal representation, but we will stick ourselves to the causal models, and henceforth when I say causal AR model, you should understand it is stationary. And then we talked about the Yule-walker equations, which are central to the estimation of AR models and the computations of PACF. Okay.